Welcome back. So today is lecture 26 and we shall continue our discussion on pseudomorphic HEMTs. Okay. So over to the whiteboard here. So in the last lecture we talked about the fact that if you want to get higher output power from this kind of devices for applications in power amplifier for instance, okay, then you need several watts of power, and as you can see, to get several watts of power, this is your different watts that are reported for different kind of pseudomorphic HEMTs, okay, gallium arsenide pseudomorphic HEMT, then the gate periphery needs to be very large. See, for instance, this is 32 millimeter of gate width, that gives you 12 watts of power when you measure between 8.5 to 10.5 gigahertz. This is X band, okay. Alright, and you get a gain of 7.2 dB with a 40% PAE. The device is biased at 7 volt because the breakdown will be around 10 to 15 volt probably, okay. So you bias at typically half the breakdown volt or lower than that, okay. But you see 32 millimeter of gate width means that the total gate width has to be 32 millimeter. So if this is your source and this is your drain, then this gate finger that comes, this is your unit gate length W, okay. This cannot be 32 millimeter of course, because the electromagnetic wave has to propagate. So this dimension W has to be much less than lambda by 10 as a rule of thumb. Typically it should be around lambda by 200, okay, as a rule of thumb. You would not find this in textbook, but if you do not keep this condition, then you will have significant phase delays as the signal propagates along the gate width. Your RF input is coming from here, RF input, and so the propagation delay will be too much along this width. You will have gradual dephasing and also attenuation of the signal that we discussed in the last lecture. Your gain will significantly drop and you will not get a working device. So this dimension of W unit has to be much lower. So for instance at 10 gigahertz, let us see, at 10 gigahertz what is the lambda? The lambda will be equal to the speed of light, which is 3 into 10 to the power 8 meter per second, divided by 10 to the power 10, which is 10 gigahertz. So that comes out to be 0.03 meter, which is roughly 3 centimeter. So lambda by 10 will be 0.3 centimeter, which is 3 millimeter. So this width of the one finger of the gate has to be much lower than 3 millimeter. W has to be around lambda by 200 or lower than that typically, okay. So which means if your lambda is 3 centimeter, then lambda by 100 will be your 0.03 centimeter, which is your equal to 0.3 millimeter, which turns out to be 300 micron. So lambda by 200 will be, so for a frequency of around of 10 gigahertz, your lambda is equal to 0.03 meter, which is 3 centimeter. So your unit gate width, so the width of one gate finger should be not more than say lambda by 200, okay. So lambda by 100 is in this case 0.03 centimeter, which is 0.3 millimeter, and that is your 300 micron. So lambda by 200 will be 150 micron, correct. So which means if you have a source and a drain and then you have a gate here, then this width W should be around 150 micron, not more. Typically people will use somewhere between 100 to 150 micron. So you will find in the literature that people have devices at 125 micron, 150 micron, etc. But if you have something in that range, you can be assured that your phase dephasing of the signal or attenuation of the signal, that depends also on the gate resistance by the way, will not be severe, you will be okay. So which means if this is only 200 micron or say 150 micron, and you need at this frequency say at 10 gigahertz you need 32 millimeter, but each finger is around 150 micron, so 0.15 millimeter, correct. So the number of finger and the number of gate fingers that you would need is 3200 by 15, okay. That is an enormously large number, okay. You will probably need around 300 fingers or so, okay, maybe 280 fingers or so. So that is an enormously large number of finger, and it is extremely difficult to fabricate devices that can go that way, So each one finger is 150 micron, then if you have 10 fingers such like that, then you have actually 1.5 mm of total gate. Okay. So to get 32 millimeter, you will probably need around, this is 10 finger. So 10 finger gives you 1.5 millimeter. Okay. So 100 finger will give you 15 millimeter, so around 200 fingers. So you need n equal to 200 fingers, you need 200 fingers to make actually 32 millimeter of gate. Okay. And that is a very large number, how can you have 200 fingers. So it is a very enormous fabrication challenge. You have to have many there is a fabrication plus design challenges also here, because if you suppose I put all this source drain, I have a big manifold like that. Okay. So these are source drain, and then in between I will have gate. Okay. So in between I will have gate, I have all these gates here. So eventually suppose I do all these gates here, correct. So I have suppose 200 finger or 100 fingers as the case may be. As I told you, this dimension must be around lambda by 200. It so happens that this dimension also should be around lambda by 200, because otherwise when the signal comes in, RF input signal comes in, it will also take time, finite time to propagate along this. So if you are far away from the input line, then you have significant phase delays, okay, and attenuation. So you have to have a total area which is around lambda by 200 and lambda by 200, or you can at least lambda by 100 or something like that. Okay. You cannot have much bigger than that, which means one cell or one device module here will be only so much, but you need maybe 50 of those. So you need to combine the power. Okay. You need to combine the cell, this is called power cell combining. You will have so many cells and you need to combine them. So what will happen is that all the cell can be combined either at the package level or at the die level, and you can leave it up to the designer, or sorry, the user, how he or she wants to combine them. But in general for lower frequencies you will have like a big bus bar or like a pad onto which you wire bond. Okay. From the input line you wire bond, and so they will feed the signals together, so that you do not have one signal propagating everywhere. Okay. You will feed the signals together in a large power bar. I will show you images of course later on. You feed them, and so that you can feed all these power cells together, so that there is no phase delay along this direction, and this of course has to be lambda by 200. Okay. So this is the concept of multi-finger device and power cell, how we combine the power cells, because you need to increase the output power, because your breakdown voltage is limited by the gate drain spacing, and so your bias voltage is also limited 7 volt. In this case you cannot arbitrarily increase it to say 20 volt bias. I cannot put the breakdown at 100 volt. Why? Because if I want to have a breakdown of 100 volt, then the gate to drain spacing, this is your gate finger, this is your drain finger. Your gate drain spacing primarily dictates, among other things also of course, field plates, everything included, and double recess. This spacing of LGD will largely dictate your breakdown. So to have a breakdown of say 100 volt, okay, and if you have a breakdown of 100 volt, you can technically bias the device, instead of 7 volt you can bias it at 50 volt. 50 volt is 7 times higher than 7, which means your output power will immediately, density will increase by 7 times, if you, that is the best case scenario of course. Now to get a breakdown of say 100 volt, you need a certain gate drain spacing. This gate drain spacing has to be enormously large to accommodate 100 volt of breakdown, and if you have such an enormously large spacing, your electrons will take a long time to go from the gate, below the gate, to the drain, which means your transit time, your cutoff frequency will reduce, because your gate drain spacing is very large. If your cutoff frequency reduces, your gain drops, but more importantly you may not even get power at 8 to 10 gigahertz if your cutoff frequency is say 12 gigahertz. If your cutoff frequency is 10 to 12 gigahertz, then you will not get any power, any gain, okay, or meaningful gain or meaningful power at 8 to 10 gigahertz. Your cutoff frequency should be around 35-40 gigahertz, ideally. So your gate drain spacing, there is a limit to the gate drain spacing you can have, so as to enable that kind of a transit time or a frequency, and so your breakdown voltage has a limit, and that is why you have a limit of 7 volt here as a drain bias, which means the breakdown voltage could be 15 volt or so. Okay. This part we discussed, but I would like to go through this again, because this is a very important concept for a multi-finger device, and I discussed this in the last lecture, so I will not go again. Essentially the gate finger width, then along the entire width of the gate finger, along this entire width of this gate finger, we consider the gate as a loaded transmission line, and we invoke the distributed model, where you have a gate capacitance in parallel with the gate resistance, and of course gate inductance, because it is like a metal, it is like a wire. So you have this distributed model, and you can see that as the signal propagates it will attenuate because of this networks of this inductance, resistance, capacitances, as a circuit, and this is each unit element, delta z, you can say delta z, each unit element, and of course you have to add them up over the entire length. So the signal attenuates and there is a gradual dephasing of the signal. That is why you have to do all these multi-finger devices with careful design. But and this is also what I discussed in the last lecture, that you have to have this kind of a multi-finger layout. Of course here there are only 3 or 4 fingers, but you could have enormous number of fingers as long as this is around lambda by 200 or lambda by 100 and this is around lambda by 200. Okay, that it's a rule of thumb in a way. There is no book probably that will mention that to you, but it's a rule of thumb. And so you can see these circles, these are via, where you etch the substrate all the way to the metal pad above and you fill it up with metal, so that you can create a ground inductance plane. You keep the back side of the wafer ground source actually. Okay, and you have this gate. You can see this gate is crossing over this source here below, that is an air bridge. So the metal will go like that, and below the metal there will be another metal that will go. Okay, we will show pictures of that. So there are different packing schemes. So this does not have air bridge for instance, but in general it is good to have air bridge. This does not have air bridge because these are via holes. These are via holes that are connecting the source to the ground below. Okay, the air bridge is to short all the source finger. For instance here you are shorting all the source fingers, here you are shorting all the gate fingers. So that shorting of the source or the gate finger etc. needs the air bridge. If you can short the source through the via to the backside plane, then you do not need air bridge. Okay, technically. So you can get away with air bridge if you have a via hole directly, that all the source should be connected together to the ground. Okay, otherwise the source, you cannot connect the source together without air bridge. That is the whole thing. Okay, so these are different packing schemes, different design layouts that are used for multi-finger devices. But while we are discussing multi-finger devices, it is also worthwhile to keep in mind that on the wafer when you measure your devices, you need to have like a CPW pads. CPW stands for coplanar waveguide, and unlike purely electromagnetic or antenna community where CPW probe pads means that you do rigorous simulation, modeling, design, analysis to actually design the different dimensions and other things of the CPW. Here we do not do that as rigorously on wafer front. It's just more like a measurement pad, but nevertheless the nomenclature is still CPW. What is CPW? It's essentially like a waveguide. RF signal is an electromagnetic signal, and electromagnetic signal can propagate in a waveguide. It can propagate in free space or vacuum of course, but for electronic application you always have this rectangular hollow tube waveguide, a coaxial waveguide. There are different kinds of waveguide, but the idea is that you bring the electromagnetic signal to the semiconductor wafer. So your waveguide on the semiconductor wafer has to be a structure which is compatible and feasible to be manufactured using standard microelectronic device fabrication technique. So CPW or coplanar waveguide is one of the many different types of waveguides. There is strip line, there is microstrip, as I told you, there is coaxial, there are so many different kinds of waveguide. A waveguide is a medium through which your RF signal or electromagnetic signal will propagate. Like there is a signal, essentially there is a signal line, and then around that there is a ground line. Okay, so signal and ground. Okay, and you have an oscillating electric and an oscillating magnetic field, they reinforce each other and they propagate. There are different modes by the way, a transverse electromagnetic mode, TEM mode, a purely transverse electric mode, right, sorry, transverse electric mode, or a purely transverse magnetic mode, etc., etc. Okay, so in a semiconductor substrate you can think of this as your gallium arsenide substrate for instance. So coplanar waveguide essentially is that there is a signal here, this is your signal line where you bring the signal in or take the signal out. For instance this could be your gate on the input side where you are bringing the signal in, or this could be your drain on the output side where you are taking the signal out, and this is ground or source, this is ground or source. So you are essentially having the RF signal coming here, but you have two grounds beside it so that the signal can reinforce with each other and propagate. Now it is not mandatory to have coplanar waveguide, but this is the most commonly used and convenient design. You can, as I told you, you can have microstrip, you can have strip line. There are different kinds of waveguides possible even in a semiconductor substrate. Some of them we will quickly discuss towards the end of this course when we talk about microwave engineering fundamentals. Okay, but CPW is a very common configuration. So you can see that this is your source, maybe I will use the red color here. Okay, this is your source, this is your source. Okay, this is your for instance drain, okay, in the output side, and this is your gate. So the gate will bring in two fingers here and here, the drain is here, source is here. Okay, so you can see the zoomed image here. there is a source, this is drain, and the gate is coming here, the gate is feeding 2 fingers here. So there will always be 2 fingers like that, okay, and you can zoom it even here. So it is gate, you can see this images are taken from the PhD thesis of Dr. Sai Charan, who was pursuing his PhD at ISC. That these devices were developed at ISC, but nevertheless more or less the GSG pads configuration would look similar across the world, in terms of how the device the pads are made. The design could change a little bit here and there, but the concept remains the same, which is you need to have a ground signal ground. So your RF probe tips will look something like that, your probe, when you bring the probe tips up, your probe tips will look something like that, okay, GSG, and then it is connected to the probe station, okay, connected to the probe station. On the other side also you will have something like that, okay, and this should be all planar. This should lie on the same plane, otherwise the tips might crash or tips might not be properly contacting. So they should be planar, they have to have the same thickness, the gate, the source, the drain, everything should have the same thickness, overall the metal thickness, okay, and then they will bring them up, of course, up here, and the total gate width here is 2 fingers. So if this is say 50 micron, so then the total gate width is 100 micron, because you have 2 fingers, correct, you have 2 fingers. So this is a waveguide, you can think of this as like a coaxial line where you have a signal and then you have a ground on the outside and the signal on the inside. If you take a slice of this, it is like that, and you open it up. So there is a signal, and on the both sides you have a ground, okay, ground and ground, okay, that is what GSG means, and that is how you measure on the wafer. But this is only for on wafer characterization. When you are going to in real world application, you have to dice the device and then package the device, or it will be in a circuit, in an MMIC or some kind of integrated circuit. So in that case the ground signal ground coplanar waveguide is not necessary, because you are going to package the device. You need to have larger pads for source and drain and gate, where especially gate and drain, where you are going to, the source is the flange, the below, you are going to have the ground inductance plane anyways. The ground, the gate and the drain has to be bonded to the package lead, the drain lead and the gate lead outside. So you do not need actually a ground signal ground kind of a configuration. That being said, for a multi-finger device you need air bridge, and these are some of the images of air bridge. I have forgotten to put the references, but I will put them. So these are images from a different PhD thesis or from a book. You can see this is the source, this is the source, in between you will have drain, this is the drain pad, this is the gate finger, this is the gate finger. So you can see that the source is connected like a metallic bridge that does not touch the gate and the drain in between. It is connecting source to source, it is a metallic short between source to source. This is called air bridge because in between the gap there is only air that has the lowest dielectric constant. So the capacitive coupling or the capacitance is the minimum in these kind of structures. You can see this is a multi-finger device, these are the air bridges you can see, okay, the scanning electron microscope images. This diagram actually corresponds to this, okay, where you have the source to source connection is happening over drain and gate, and this is actually this, where you can see that there is a gate, this is the gate. So the gate is coming on the same line here, but the source is going over the gate. Can you see that source is going over the gate? So this is the air bridge here, the air bridge, okay, and this is of course drain. So the drain has no problem with any bridge or anything, but the source is going overhead. So the air bridge process recipe, the development of the process steps is not very trivial, because you need to have a very carefully optimized process such that the bridge, the air metallic bridge, does not collapse when you subject the sample to processing or annealing or some kind of an ultrasonication, grinding, polishing, because you need to thin the substrate eventually, and many of the substrate thinning happens after the air bridge is put, okay. So it has to be mechanically stable, and so it is not very trivial. The process will involve electroplating by default. You will have to first define something called post. So the metallic line, it is the wafer for instance. So you will have to have post, and then you have to have a seed layer come up, a seed layer of a metal should come up, a gold seed layer, and on top of you will of course have photoresist to define, and then you have to have the metal deposited everywhere, and then you have to remove the photoresist from below, so that what remains is a bridge between two posts. So this is a post, you can see this is actually the post. It is not very high, so you cannot clearly tell it, but this is a metallic post on the source, this is a metallic post on the source, okay, and in between they have the drain and the gate. So you have to fill the bottom with the photoresist, the metal bridge will be deposited on the photoresist, and then you have to dissolve or wash away the photoresist so that it remains hanging on depth. Okay, that is the air bridge. It is a very important thing, and you can this span of this width of the height of the air bridge could be few micron, typically 4-5 micron. This image is also taken from a book, the book that I am mentioning in the next slide. Probably I have not mentioned it here, but I will do that anyways. This is from John Walker's book, Handbook of RF and Semiconductor Devices. You can see what it shows here is the measured, experimentally measured cutoff frequency FT versus unit gate width. You remember I told you about the unit gate width. If this is your source, this is your drain, this is your unit gate width. So 100 micron, 200 micron, 300 micron, 400 micron, 500 micron. So in general, as you can see that as the unit gate width increases, so suppose this was 100 micron, and I have another transistor where the unit gate width is 200 micron. This is 200 micron source and drain. Okay, if this is 200 micron source and drain, the cutoff frequency decreases. Okay, you can see with higher gate width the cutoff frequency decreases. Very interesting. Okay, and what are these? These are different number of gates. So these are 8 such fingers are there. This is 10 such fingers, 12 such fingers, and 14 such fingers. Okay, so you can see that as the number of finger increases, as the number of finger increases, your cutoff frequency comes down. Your cutoff frequency reduces as the number of gate finger increases, which means as your number of gate finger increases, the signal has to propagate more. So your gain will reduce, which is not shown here. Your cutoff frequency also will reduce. You can see that very obviously. So the cutoff frequency will reduce as you increase the gate width. It has to propagate more, of course, and it will also reduce if your gate, if the device lateral dimension is higher, which means the number of gate fingers is very high, then also signal has to propagate and bigger devices have bigger parasitics, of course. So your cutoff frequency comes down, your gain also comes down similarly, Fmax also comes down similarly. So this is a very important concept that or observation, because although you can do a detailed mathematical analysis on the behavior of the cutoff frequency or gain as a function of gate width and the number of gate finger, but the most popular or the common approach or the more effective approach is to experimentally fabricate the device and measure, because that will give you the actual feel for parameters like gain or cutoff frequency that changes. Okay, so that is about this multi-finger devices, and whatever we are talking about here is in the context of pseudomorphic HEMT power devices. This is what we are talking about, but is also this concepts GSG and everything else applies to gallium nitride HEMTs, applies to gallium arsenide MOSFETs, MESFETs, etc. Okay, but this was in the context of our pseudomorphic HEMT for power application. I talked about these absolute powers that you are getting and this absolute gate peripheries that you are using. Okay, and gain of course is output power by input power, both RF input power output power. So this is the air bridge and this is the cutoff frequency. And so the final thing in today's lecture is that, as I told you in a few slides before, to actually get very high power you need to combine a lot of devices. So you can see this is a 100 watt device which is an L-band. L-band stands for 1 to 2 gigahertz. Okay, 1 to 2 gigahertz, 200 millimeter. The total gate width is 200 millimeter. Can you believe that? So this is that 200 millimeter device that gives you 100 watt of power, which means you are getting 100 watt for 200 millimeter gate width. You are getting 0.5 watt per millimeter at L band at 1 to 2 gigahertz. That is the power density you are getting. So that is why you need 200 millimeter of gate width to get 100 watt of power. You can say, see, this is one module, this is one cell, this is one cell, and this is one cell. They are combining the cells. Okay, each cell will have so many fingers. Now you can leave it up to the end user to design the combination, how they want to combine. They want to take they want to take wires out, for instance, or they want to use via holes. I mean you can talk with the way the foundry works is they use it, talk with the end user how they want to combine the power at the end. Anyways, this is a 60 millimeter L band device again. This is a C band device. C band stands for 4 to 8 gigahertz. So here you are going to deliver power at 4 to 8 gigahertz, which means your gate length will be shorter than a L band device, and also your lambda is shorter. So this dimension and this dimension will be also shorter. So you can see there are also different cells here that people are combining. Okay, this is a proper power combining in a MMIC. MMIC stands for microwave monolithic integrated circuit, where you have all the components, passives, actives, everything together on the same die, fabricated in the same process run. You do not bring discrete components and put them together. You have an inductor, capacitor, transformer, etc. Everything is fabricated together with the transistor in the same process flow on the same die, monolithic. It is a microwave monolithic IC. Okay. So, in that you can combine power. So, this is a power combiner, you can see that this combining power. You can combine power at the amplifier stage, at the stage level you can combine power to get more power, and these are structures for evaluating the power cell. So, if you make this giant structure and it does not work, you do not know which part of the cell did not work. So, what people do is that they have a discrete cells like that which they are evaluating. They will evaluate the discrete cells thoroughly and then they will combine, and then they will make a mask to combine them. So, here you can see this is the G, this is on wafer. So, you can see this is a G and then S and then G, G and then S and then G. This is your probably gate, that this could be your gate, this could be your drain, okay, or vice versa. It is not very clear here. Similarly, same here. So, you qualify each unit module or unit power cell with many fingers. You get the desired power, gain, frequency, etc., and then you translate them into this large multi power cell manifold where you combine a dozen of them, for instance, to get to 100 watt or 200 watts of power at frequency. But this becomes increasingly difficult as your frequency increases, because at higher frequency your lambda decreases, and so your overall device lambda by 200 it shrinks. So, you need to combine too many cells and it becomes too difficult. So, higher the frequency, lower is the power requirement in general, okay, in general, because it is very difficult to get power. So, you will probably find 1 kilowatt or 500 watt devices that are available in the market at 1 or 2 or 3 gigahertz, although you cannot buy them because of import restrictions. Okay. However, it is very unlikely to find, say, at W band or V band 60 gigahertz, 94 gigahertz W band, you will not find 1 kilowatt or 500 watt devices that often. It is very difficult to get that kind of power levels at that high frequency. So, you will get reduced device power at higher frequency. So, in fact, for W band, which is around 94 gigahertz, at that range, your gate finger, this W will be much lower. Actually, it will be much lower. It could be 15 micron, 20-25 micron, now no more than that. So, you understand. So, it's very as you go increasing the frequency, this dimension becomes less and less. Okay. So, that's something we need to keep in mind, but this is all in the context of power amplifier. If your pseudomorphic HEMT or any MESFET or FET is going to be used in a power amplifier, then these are the basics that are important to understand before proceeding ahead. Okay. So, with that we will come to a conclusion to this lecture 26, where we basically had discussed about pseudomorphic HEMTs and took a detour to understand power cell, multi-finger devices, via hole, air bridge process. Okay. And so, in the next 2 lectures remaining for this week, we will talk about low noise application of the pseudomorphic HEMT. We will also talk about metamorphic HEMT, we will talk about indium phosphide HEMTs, and we will end this week with the advent of gallium nitride HEMT. Okay. So, thank you for your time. I will see you in the next lecture.